Okay, good morning, everybody. Let me go to full screen. Okay, I can still see everything. So what I'm thinking of talking about this morning, and I'm hoping this is going to be useful for you, are probes of the dense matter equation of state found in the neutron star interiors, introduce you to various methods that we've been using over the years, and just leave you with where we are today and what are some open questions. So I'm going to start by saying that the cold dense matter equation of state is a hard theoretical problem. So there are many different ways of understanding the interactions of matter at high densities, many different computational approaches, but none of them are conclusive and none of them are easy in terms of incorporating the effects of both nucleons and quark degrees of freedom or other particles that may appear in neutron star interiors. And to introduce you to this zoo, what I would like to show you is a pressure density diagram from the annual reviews article that I wrote with Paula Frere in 2016, compiling the many different nucleonic and other equations of state that have been calculated to date, all of them with their various codes here. And what you can see here is that this is a couple orders of magnitude in pressure, an order of magnitude in density. And there is a huge difference in the range of pressures that are predicted for a given density for a neutron star interior. For reference, this is the nuclear saturation density. But of course, we are not at nuclear saturation at symmetric matter. We are at neutron-rich matter. So that also introduces a large amount of uncertainty in what it is that we should be using for the neutron star interior composition pressure at a given density. Luckily, neutron star observations can help because there is a very nice mapping going from this equation of state space, whatever pressure you have at a given density and its functional form, tell me, and I can solve the relativistic structure equations, the Tolman-Oppenheimer-Volkoff equations, and tell you what the mass radius relation for that object with that equation of state is. So if you want to go from the left to right, that's a very well-established problem. For each one of these curves, we can establish a mass radius curve. What we're interested in doing, though, is to go from the right to the left. So tell me the mass and the radius of the object, and can I use that to infer the equation of state? And indeed, this is possible. The equation of state down here is not really pinned by neutron star observations. It's pinned down by more laboratory experiments and theory. You see that there is a region where they agree. And then the types of things that we can use are, let's say that we have the mass radius measurement for several neutron stars. As you can see, if they trace out a particular curve here, then there is a parametrization that we can use in order to map that, either using a direct mapping or some Bayesian scheme into an equation of state on the left. And then pulsar masses, especially if they are high, they can also be distinguishing in terms of what a particular mass equation of state can or cannot reproduce. That's because for each one of these curves, as you can see, there is a maximum mass that's predicted that's different for given the amount of pressure, so how much mass it can support relativistically. And because of that, if we find, for example, a pulsar that is above one of these curves, then we can say, well, that equation of state can't be correct. So we're going to employ this mapping. And what I want to do this morning, even though the time is limited, I'm really hoping that I can introduce you to some of the methodology and not just the results, so that you can go and do further reading if it's of interest to you. I'm going to describe to you 4 different probes of the neutron star equation of state. The first one is going to be pulsar masses. How do we measure them? What do we know so far? The second and third are going to be using X-rays, neutron star radii measurement, using 2 different methods in X-rays. And the fourth one is going to be how do we use gravitational wave signals and tidal deformability in order to pin down the equation of state. There is also a moment of inertia measurement from the double pulsar, but it is not constraining yet. I will briefly mention it, but it's not something that we can actually employ as a constraint right now. By the way, please feel free to stop me if there are clarifying questions that you need to ask, and we will leave some minutes for questions at the end as well. So measuring neutron star masses through pulsar timing, if the pulsar is in a binary, the first thing that is measured is what is called the binary mass function. As soon as you know the period and the projection of the pulsar's orbit on the observer's line of sight. But this in itself is not enough to get the pulsar and the component mass. In order to go beyond this binary mass function, one needs to measure one of, at least one, but really two of the relativistic effects that are typically parameterized as the post-Keplerian effects on the binary orbit. And I'm not going to go into detail, but this is just a good way to see how these various relativistic effects, advance of the periastron if it's an elliptical orbit, and the Shapiro delay if you're looking more or less edge-on on the binary plane, and there's an additional time delay introduced by the companion passing in front of the pulsar and vice versa. Orbital period decay, PB dot, that we've measured in the Hulse-Taylor pulsar for the first time. So to go beyond this mass function and get the component masses, one needs at least two more constraints in order to solve for the two. This is the best known example of how these post-Keplerian parameters lead to what is called a mass-mass diagram. But the double pulsar is very special. It's the only case where not only does the neutron star have a neutron star companion, but we've observed both of them as pulsars. In addition, it is a very edge-on orbit. We're looking at it at 89 degrees inclination. So it is this amazing system where not only can you measure enough post-Keplerian parameters to determine the masses, but you measure post-Keplerian parameters for each of the pulsar. Therefore, you can also do a GR test and all sorts of tests of how the two match with one another. So as you can see, there is all of these post-Keplerian parameters measured, leading to this extremely precise mass for the two components. In reality, that's in general, that's not how it happens. Most pulsars have only two post-Keplerian or even less components measured. So I'm going to go straight to the results that are of interest to us, what I'm calling the record holders in mass. If the pulsar mass is 1.4 or 1.5 solar masses, it is less interesting because almost every equation of state can reproduce that. So what are the record holders from pulsar timing? There is a 1.92 plus or minus 0.04 solar mass, initially a 2 solar mass system that was revised down later on. This is from the Shapiro delay. There is a second record holder at 2.04 solar masses from Antoniadis et al., but this has only one post-Keplerian parameter measured, and in order to get two individual component masses, the additional constraint comes from the spectroscopy of the white dwarf. So it's not the same caliber measurement as pure pulsar timing, in my view. And the latest record holder is 2.14 solar masses with these error bars that you see here. Again, a Shapiro delay measurement. And this is the first data set from Nanograv. We'll wait to see how this gets revised with future data. Any questions on pulsar timing? So this is where we are, right around 2 solar masses. Just a little bit above seems to be the current record holders among many, many that have been measured. Okay, let me switch gears and take you to the radius measurements then. As I said, I'm going to describe two different methods. The first one is basically, how do you make an HR diagram for neutron stars? What you do is a spectroscopy of the surface emission. We're going to go to sources where there is emission from the surface. And if we were doing this for a normal star, the emitting area would be simply the flux times distance square over sigma t to the fourth. And you would correct this using the model of the atmosphere, just like we do in stars, to go from the measured spectral temperature, or the so-called color temperature, to the effective temperature, that's the radiation temperature. But it's not a star, it's a neutron star, which means it is very compact. Otherwise, you wouldn't be having this TCAN grant to work on this difficult problem. Of course, the space-time evolves and in mergers, but even here, the compactness is so strong that the neutron star lenses the emission that originates from its surface, which to lowest order would introduce a correction like the one that you see in the parentheses here. If it's a spinning neutron star, which most of our sources are, there are additional corrections that we solve for numerically. So you take the surface of the star, build a model for its atmosphere, calculate its space-time as a function of spin, quadrupole moment, etc., and effectively use that to measure the emitting area of the surface. However, you can't do this for any source. You really need to go to a source where there is emission from the surface, from the whole surface, and nothing but the surface. So for example, if you went to a radio pulsar, the emission is completely dominated by its magnetosphere. The fact that you see it as a pulsar means that the surface is not a uniform temperature. So these are not the sources that you would go to. But luckily, there are some sources where there is little to no accretion disk emission. So this is a neutron star in a low mass X-ray binary. The neutron star has a low mass companion. It is accreting through a disk, but what you want is that accretion disk emission to not get in your way when you're looking for the emission from the surface of the star. Little to no magnetospheric emission. You want low magnetic field so that there isn't the surface anisotropy in the emission. You see the entire thing uniformly emitting. And the way you can do this in these neutron stars and low mass X-ray binaries is you look for this thermal emission from the surface, either during quiescent episodes in between accretion, where the accretion rate has really fallen, and all you see is the re-radiation of that stored heat from the surface, or doing thermonuclear bursts, where the accreted material hydrogen-helium mixture ignites and goes unstable. The triple alpha basically engulfs the entire surface. And for the duration of the burst, which tends to be of the order of 10 to 50 seconds, the emission that you see comes entirely from the surface and nothing else really. So to show you a thermonuclear burst example, what I have here is the evolution of flux, the temperature, and basically the flux over sigma t to the fourth in the middle panel, this emitting area as a function of time. As I said, this particular burst is of the order of 40 seconds. So the flux suddenly rises when you're looking at it with an X-ray telescope and decays over seconds time scales. And in the meantime, the normalization rises and then stays constant for a while. So just like we built HR diagrams for normal stars, if you plot flux here and color temperature increasing to the left, again in a normal HR diagram, what you see is that for sources where you see repeated events like this, they follow this nice track that is the t to the fourth line, and the normalization of this gives you the radius of the star. And because you have repeated data, you can account for the spread in this as your uncertainty in your emitting area. This would give you a combination of mass and radius, but the nice thing about thermonuclear bursts is that some of them also reach the Eddington limit, where the outermost layer of the star actually gets lifted off because of the radiation pressure. This is the expression for the simplest Eddington limit, again with the GR correction here. And if you look at the normalization versus the color temperature here, if you see repeated Eddington limited phenomena, you can use this peak flux that the burst reaches as a measure of this Eddington luminosity, and it gives you another combination, measurement of the combination of mass and radius. Using these, you can break this degeneracy between the mass and radius. And here are the 6 burst sources. And the one that I didn't describe, but it's the exact same type of thinking, but only during quiescence. So as you can see, the uncertainties are a little bit bigger for quiescent sources because we don't have the Eddington limit. A large number of people who worked on this, source by source, basically getting the mass and radius measurements from this surface spectroscopy method. And we have a total of 14 where we say we have been able to determine the mass and radius with these uncertainties that you see. And they cluster around 10 kilometers, and here again, around 10 kilometers, some of them are quite uncertain. So what we can do is put these together and ask, in this inversion that I introduced in the beginning, okay, now I have all of these mass radius measurements. If I combine them, what can I say about the neutron star equation of state? The blue band here shows you the best fit mass radius relation that explains all of these 14 sources. And it also takes into account all the nuclear experiments, the constraints that come from nuclear experiments in laboratories. So this is the band that you would deduce from that. At 95% confidence interval, it's about 10 to 11.5 kilometers. And this equation of state is consistent with a maximum mass of about 2.05 solar masses. If we go the next step and say, okay, what's the equation of state that you can infer using this parametric form, then again, this blue band would tell you this is the equation of state that describes the neutron star interiors coming from the X-ray spectroscopy data. What does it say? It says that the dense matter equation of state is soft. That's a term that we use often to mean that the slope of the pressure density relation actually is a little bit softer than some of these, for example, compared to this slope here, where the pressure rises more strongly. So the polytropic index is smaller than an equation of state like that. And what are typical things that soften the equation of state? Well, introducing new degrees of freedom so that the energy doesn't rise as quickly. For example, this could be quarks, this could be other types of particles, but it also implies low isospin symmetry energy. What that means is that the penalty you pay to go to non-symmetric matter, so non-unequal numbers of neutrons and protons, is small. So these are all things that we have compiled from the, or we have inferred from the compilation of those 14 sources. How am I doing with time? So, okay. This is not a settled problem. There have been criticisms of this method in the literature. For example, that the effect of accretion is not as small as we think, or the surface modeling that we use in order to get the spectroscopy, this temperature right for the surface area measurement isn't the best, or it doesn't work for all the sources, so we should select a subset, etc. So I don't want to give the impression to you that it's a settled problem. There has been a lot of back and forth in the literature on how to improve it. The second method of X-rays, again, uses neutron stars, but in this case, you specifically look for sources that are pulsars. And the reason for that is when you have a pulsar, the magnetic field footprint, the polar cap on the neutron star surface, as it rotates, the observer at infinity sees, of course, a particular pulse profile that is traced out by this emission pattern on the surface. So if you look at this pulse profile, because the emission that originates from the surface is again lensed by the neutron star itself, you can get a combination of the mass and radius or the compactness of the neutron star through this method. The mission that was specifically designed to target such sources and to get this pulse profile with very good accuracy is called NICER, Neutron Star Interior Composition Explorer. And it has been since 2017 collecting data on key pulsar targets and thermonuclear bursts. The first analyses from NICER data, there are two sets of papers on two sources. One source, 0030, does not have an independent mass measurement through timing. Therefore, you see these correlated uncertainties in mass and radius. And I want to also point out that this is a very, very large scale on the x-axis, going from 10 to 20 kilometers to basically neutron star radii that aren't really interesting. But this is the first data set of the pulsar analyses that gives you a constraint that is between about 10 and 16 kilometers at a few sigma. And this is the second source, 0740, where there is an independent mass measurement. That's why you see the contours of the radius uncertainty parallel for this given pulsar mass. And that again gives you about 10.5 to about 14 kilometers. So both of these analyses find neutron star radii that are larger than the ones that I just showed you through the first method of surface spectroscopy. There are also questions and systematics that are associated with NICER results. Here is my compilation of these outstanding items. When we fit the light curves, as I showed you here, even when you have very high signal to noise, you need a very large number of free parameters. The size, shape, and latitude of each of the spots. And here is a figure from one of the Miller et al. Papers that shows that 3 elliptical spots were needed in order to fit at various inclinations, latitudes were needed to fit that pulse profile. You don't know observer's inclination a priori. You don't know the beaming function of radiation. You don't know your background because NICER does suffer from energy-dependent backgrounds. And more importantly, you don't know your foreground, which is the magnetospheric emission. These are pulsars after all. So in order to get to the surface emission, you need to subtract the magnetospheric component, which is typically assumed to be a power law. But the results are sensitive to the subtraction of that component pretty seriously. In addition, there are deep heating models that are used in these analyses, but the polar caps are hot because of particle bombardment onto the surface. So there's just more that you will see coming out of NICER, maybe better analyses or more sophisticated models, but some of these are, I think, going to be just intrinsic uncertainties associated with these methods. Last but not least, the golden standard is the tidal deformability that we can measure from neutron star mergers. It suffers the least from systematic uncertainties of the other methods in terms of getting at a radius. The downside is we have a total of 1. And why don't I say 2? Because there's only one event, 170817, that has high enough signal to noise ratio to actually infer the tidal deformability during the in-spiral. So why does this encode any information about the neutron star interior? It's because neutron stars of different compactness and different radii have different deformabilities as they are in the tidal gravitational field of the other source. One can infer from the waveform the how deformable the neutron star was as it was approaching its companion. However, you don't infer the deformability of a single source, of a single component. What you read off from the waveforms, or what you can infer from the waveforms, is called the effective or the binary tidal deformability, which is a mass-weighted average of the two tidal deformabilities of the two neutron stars, λ1 and λ2, in this notation. 3 minutes. Perfect, thank you. Okay, so we have a measurement of lambda from 1708-17. As you can see, it peaks at pretty low values. Low values are more compact stars, less deformable. But what we've done, and this is Carolyn Rathel's work, she's going to talk to you later today. She was a graduate student with me before moving on to Princeton. What we've discovered is a new universal mapping between this tidal, effective tidal deformability of the binary and the radii of the components. So one way to see this would be, this is the tidal deformability as a function of neutron star radius for different component masses that are allowed given the chirp mass and the binary mass ratio for 1708-17. So what this plot is meant to show you is that the effective tidal deformability is quite insensitive to the individual component mass. So each of these symbols vary the component masses given the chirp mass between 1.36 and 1.60. And as you can see, there is a huge difference when you change the neutron star radius with these different equations of state. But there is a very, very small difference if you change the mass. So this basically says, if you have a gravitational wave event where you measure the binary tidal deformability and a precise chirp mass, and you don't know the mass ratio very well, this Q is uncertain, allowing different mass components, it doesn't matter. There is a beautiful mapping between the tidal deformability and the stellar radius. Here we're showing it a different way. So again, this lambda tilde is a function of one of the component masses, and you can really see that independent of the component mass, a 10 kilometer will map to lambda tilde of 150, 11 kilometer will map to 260 for this chirp mass, etc. Very nice separation with radii. And we've also developed an analytical understanding using quasi-Newtonian deformabilities of why there is this strong mapping and very weak dependence on the mass ratio Q. So what that means is that if I have a posterior for the effective binary tidal deformability, we can turn it into a posterior for the radius, which is what we've done here. So for reference, this is the X-ray data from the first method that I showed you. And these are the posteriors that you obtain from for radius from 1708-17 using this mapping between lambda tilde and radius. These two are in pretty good agreement. The gravitational wave itself gives a highest probability density interval of 10.2 to 11.7. And so these two agree, but there is tension between the gravitational wave result, this one measurement that we have so far, and the nicer results that have been published so far, which find quite a bit larger neutron star radii. So I'm just going to put all of this together and leave you with the opening slide that I already showed you. Where we are is that we have different probes of the neutron star interior. And so far, the pulsar mass data, the one LIGO data from tidal deformability, and the X-ray data from surface spectroscopy agree with one another and point to this band in the pressure density relation. And nicer analyses find somewhat larger radii that are in tension with these results. But of course, it's a developing problem that hopefully in the next 5, 6, 7 years of data is going to help with even more. So I'm going to stop there and answer a few questions.
Okay, thank you very much, Feryal, for extremely interesting talk on the constraints on equations of state. As we did yesterday, we'll ask people who have questions to, quote, raise their hands on the participant screen. And see, I see a couple already. Okay, so Carlos, you have to begin?
Yes, hi, thank you. That was a very nice and clear talk. Sorry if I missed, you already spoke about this, I missed the very early part of your talk. I was wondering about glitches. If glitches in pulsars can give you also some information about, well, radii and equation of state.
That's a very good question. When I listed the various probes and I said the moment of inertia, I could have included glitches there too. What the glitches tell you is the relative moment of inertia of the core to the crust. So the prevailing theory of glitches is that there is differential rotation introduced because of superfluidity in the core and the crust. And at some point, this differential rotation basically resets. So the star starts rotating as a uniform object again, uniformly rotating body again. So the thing that glitches give you is this relative moment of inertia of the two components and not really the equation of state of the core. But as an indirect probe, of course, that's still useful.
Okay, Salvatore.
Yeah, I hope I can be heard. Thank you, Priya, for the nice talk. I have a question on the universal relation you mentioned at the end. So this may be for Caroline later, in which case I will wait, but I'll ask just in case. You mentioned that it's not very dependent on the primary mass. Can I ask if it's more dependent or dependent at all on the chirp mass?
Yes, it is definitely dependent on the chirp mass. So oops, I should try to go back. So all of these are for a fixed chirp mass. So the trick to this mapping is that you use lambda tilde and you use the chirp mass, but you vary Q, which it's very insensitive to. So when you do the expansion of lambda tilde, there is a quadratic dependence on 1 minus Q with a very small coefficient up front, but there is definitely a dependence on the chirp mass. I don't think I have the full expression here, but it's in Raythel et al.
Thank you.
Okay, Wolfgang's next.